The space shuttle was the most complex flying machine ever built. On every single mission, it carried something staggering, 2 million liters of liquid. To put that in perspective, that's enough to fill 40,000 cars to the brim. Or think of it this way. If you started pumping that fuel into your car, right? Now, at normal gas station speed, you'd be standing there for 23 days straight. But here's the question that almost nobody asks. Where does all that fuel actually go? Because when the space shuttle landed, when it touched down on that runway, it arrived practically empty. Almost nothing left. So, what happened to it all? That's what we're about to find out. If you ask most people to imagine the space shuttle, they picture, well, something like a big plane with a giant gas tank inside. Like your car, but bigger. The fuel goes in the back, the astronauts sit in front, and off it goes. Simple, right? But here's the thing, that mental image is completely wrong. The space shuttle doesn't work like your car. It doesn't work like any plane ever built. The reality is far stranger and far more interesting than most people realize. To understand where the fuel goes, we first need to understand where it actually lies. The space shuttle wasn't one vehicle. It was 3 vehicles bolted together, pretending to be one. At the center, the orbiter, the part that looks like a plane, the part the astronauts ride in. On each side, 2 solid rocket boosters, the white candles providing brute force. And towering over everything, attached to the belly of the orbiter, the external tank. That orange giant is where our mystery begins. Because that tank, that's where 96% of all the fuel lives. Not inside the orbiter, not in the boosters, in that orange cylinder that gets thrown away. Let's talk about this orange giant. The external tank stands 47 meters tall. That's taller than a lying down Statue of Liberty. It weighs 760 tons when fully loaded, and 735 of those tons are fuel. Inside, it's divided into 2 sections. The bottom 2/3, that's the liquid hydrogen tank, 1.5 million liters at minus 253 degrees Celsius. Cold enough to freeze air. The top third is the liquid oxygen tank, 500,000 liters at minus 183 degrees. Together, they form the largest cryogenic fuel tank ever flown. And here's the crazy part. It's not even pressurized like a soda can. It needs constant venting, or the fuel warming up would turn it into a bomb. The orange color, that's not paint. It's the insulation foam itself. Painting it would have added 600 kilograms, weight they couldn't afford. T-minus 10 seconds. The 3 RS-25 main engines ignite first. They're getting their fuel directly from that orange tank through pipes 45 centimeters in diameter. The flow is staggering, 1,800 liters every single second. That's a swimming pool every 25 seconds. But here's what most people don't know. Those main engines aren't even the main thrust at liftoff. They're producing about 25% of the total power. The real muscle comes from the solid rocket boosters, those white rockets on the sides. They provide 71% of the thrust. Together, this stack generates 7.8 million pounds of thrust. And in that first minute, while the shuttle is still fighting through the thickest part of the atmosphere, it's burning through fuel faster than you can blink. About 1 minute into flight, the shuttle hits something called max-Q, maximum dynamic pressure. This is the moment of maximum stress on the vehicle. The atmosphere is still thick, the speed is building, and the structural loads are at their peak. The shuttle actually throttles down its main engines here to reduce stress, then throttles back up once through. Meanwhile, those solid rocket boosters are burning their own fuel, a rubbery solid propellant that can't be throttled or shut off. They burn until they're empty 2 minutes into flight. Then, at 45 kilometers up and traveling 5,000 kilometers per hour, they separate. They're done. They parachute into the ocean to be recovered and reused. But the external tank, it's still attached, and it's still full of most of its fuel. From SRB separation until main engine cutoff, the RS-25 engines drink from that external tank like a fire hose. Remember, 1,800 liters per second. For another 6 minutes, the fuel level drops visibly. Inside the hydrogen tank, the liquid sloshes and churns as the vehicle accelerates. The tank walls flex and groan. The engines themselves are running at 100% power, then throttle up to 104% for the final push to orbit. Each engine produces 418,000 pounds of thrust. Together, they're throwing the shuttle faster and faster. By the 8-minute mark, the vehicle is traveling at 28,000 kilometers per hour, 23 times the speed of sound. But now there's a problem. The fuel is almost gone, and the external tank is dead weight. At 8 minutes and 30 seconds, Main engine cut off. The engine shut down. The vibration stops. For a moment, silence. Then, explosive bolts fire. The umbilical connections sever. And the external tank, that 47-meter, 760-ton orange giant that carried humanity to space, is released. It drifts away from the orbiter, slowly tumbling. Inside, just a few drops of fuel remain. Most of it, 735 tons, became exhaust, became thrust, became the velocity that put the shuttle in orbit. The tank itself is now worthless. A $40 million piece of space hardware with no purpose. It will re-enter the atmosphere in about an hour, somewhere over the Pacific Ocean. It will hit the air at 25,000 kilometers per hour. The friction will heat it to 1,600 degrees. The aluminum will melt. The foam will vaporize. In 8 minutes after separation, it will disintegrate completely, raining debris over 1,000 kilometers of open ocean. But wait, the orbiter isn't done with fuel yet. Remember, it's still in orbit. It needs to maneuver. It needs to change position. It needs to come home eventually. For that, it carries its own secret fuel supply. 2 spherical tanks hidden in the aft fuselage, right behind the vertical stabilizer. These contain something called hypergolic fuel, specifically monomethylhydrazine and nitrogen tetroxide. Here's why it's special. These two chemicals ignite spontaneously when they touch each other. No spark needed. No igniter. Just contact and instant combustion. The shuttle carries about 20 tons of this stuff. It's used by the OMS engines, the orbital maneuvering system, for big burns like circularizing the orbit or starting the descent, and by the RCS thrusters reaction control system for small attitude adjustments. Every time the shuttle rotates in space, every time it changes orientation, it's firing these thrusters. During a typical mission, the shuttle uses this fuel constantly. Docking with the space station. RCS thrusters firing in bursts, pointing cameras at Earth. Tiny adjustments. The big OMS burns happen only a few times, maybe 2 or 3 per mission. But those small RCS firings, hundreds, thousands, each one uses a little fuel. By the end of a 10-day mission, that 20 tons has shrunk to almost nothing. Maybe a few hundred kilograms remain. Just enough to deorbit. Just enough to come home. To come home, the shuttle needs one last OMS burn. The deorbit burn. About 3 minutes of firing to slow down enough to drop out of orbit. This single burn uses most of the remaining fuel. When it's done, the orbiter is committed. There's no abort. No second chance. It will re-enter. Re-entry is the most dangerous part. The shuttle hits the atmosphere at 25 times the speed of sound. The heat shield glows at 1,650 degrees. Plasma surrounds the vehicle. No engines now. It's a glider. A 100-ton brick with wings falling from space. The RCS thrusters make tiny corrections, but they're nearly empty now. The landing is legendary. No engines. No fuel for go-rounds. One shot. The shuttle drops like a stone, then flares at the last second, touching down at 350 kilometers per hour. When the wheels hit that runway, the vehicle weighs about 100 tons. Remember the launch weight. Over 2,000 tons. Less than 5% remains. So where did the fuel go? The 2 million liters. It became exhaust. It became heat. It became the velocity that lifted 2,000 tons to space. It became maneuvers that docked with the space station 135 times. Every drop was accounted for. Every drop was transformed into something else. The external tank became atmospheric dust over the Pacific. The hypergolic fuel became thrust in orbit, and when the shuttle landed empty, it was by design. Today, SpaceX is changing this equation with Starship. There, the fuel tanks stay attached. There, everything comes back. But the space shuttle was a bridge between eras, the first reusable spacecraft, even if imperfect. $40 million of external tank turned to vapor every single flight. 135 flights. That's over $5 billion in tanks alone, raining down on the Pacific. But it bought us something priceless, the International Space Station. 30 years of science, and the knowledge that we could build machines this complex, this audacious, this capable. Every liter of fuel was worth it. If you enjoyed this journey through Where the Fuel Goes, subscribe, leave a comment with your favorite space shuttle fact, and let me know what part of space exploration should we explore next.